Just a little bit about us. We're the Southwest Center for Occupational and Environmental Health. We do research, training, outreach, and continuing education on occupational health. We do industrial hygiene, environmental medicine, epidemiology, total worker health, and we have pilot project research. Save the date. So we have many continuing education events coming up. We have our Occupational Medicine Journal Club, which is virtual, actually hybrid, can be in person or virtual. We have our Environmental and Occupational Health Science Research Seminar Series, another hybrid event where you can attend in person or virtual. We have our Physicians for Social Responsibility Series coming February 26th. That is a virtual event. And April is the big Gulf Coast Chapter Professional Development Conference here in Houston, Texas. Jan will talk a little bit about more of it in her presentation, but that is a big one-day conference that we have every year. You can visit us at our website at SWCOEH.org. So I will stop sharing and we will give the stage to our first speaker, Dr. Marcus Sanchez. He is he is with Shell Oil, and he is in occupational health safety and industrial hygiene. He holds a master's degree in occupational health and an MBA from Texas A&M. He is a CIH and a CSP, and he is the health manager for ventures and renewables. So please, everyone, welcome Marcus Sanchez.
Hi, thank you, Serena. I hope you all can hear me okay and also see me.
Yes, very good.
Thank you very much. Thank you for this opportunity. Always a pleasure. My honor to be here and talk to you about renewables and from our perspective in the energy sector, and particularly my role in Shell is to manage the interface between the human health and this energy transition component that is so critical for our society nowadays, and also identify opportunities for us to, add value, protect our people, and go through this transition period with the ambitious goals we all had: clean energy, healthy environment, healthy people thriving through this process. I'm going to share my screen, Serena, if that is okay, or can I start now, or do you need a few more minutes?
Yes, please. Go ahead.
Okay, good. I'm going to share my screen. Grateful you can tell me you can see the presentation here. And the other thing I'm going to do is to put the video off to, I noticed this is better for my internet connection, but I'll be willing to reconnect the video if needed. So can you see my presentation? Just give me a shout or send me a palm up. That would be good. All right. Well, we are going to talk about this content here, but definitely we can address other components in the discussion part, or if you have questions or comments, definitely happy to address that. But I think that it's important for us to define the landscape in renewable energy and what that means, what that includes. I mean, how are going to get those projects connected to our existing facilities or our existing sources of energy. Go through the health, safety, risks. What is the risk profile? What are the risks associated with the new technology? I think that's also another important component to identify areas in which we can add value as HSE professionals. Recognize on emerging technologies. Some of these technologies not so new. They have been around for a while. The use of that technology in connection with these solutions for the energy transitions is what is a new approach. And in that new approach, we see different risks, different interfaces, different challenges and opportunities. And we will discuss a little bit that through a couple of examples. And when can we definitely identify areas to protect our workforce, which is our, duty, is non-negotiable and is the key part in our work. The bread and butter here is actually protect our people. Let's go to the landscape briefly here. So this is an amalgamated, complicated, and somehow large portfolio of renewable components. I'll try to summarize here the key areas, but definitely there are other things emerging. This is a moving target, and we are definitely welcome technology almost every year that will be connected to what we already have and what we already know. But basically, the power generation is the key component here, is large, and that includes the onshore wind, offshore wind as well, the solar farms and the power plants. The reason we include here the power plants, you may say, well, power plants have been around, since electricity was somehow canalized to the customers a century ago, or more. But, the key component here in the new landscape is that these these energy generation plants that have been around for a while can definitely function with cleaner energy, can function with low carbon energy, and can be a better solution now for customers or for the community as we connect these with the grid and as we connect these with low carbon fuels, as also we open markets opportunities in which we have or we can deploy other sources of clean energy. So we definitely have it here. We call this presentation energy transition, so they will be there for a while, along with other sources of energy like fossil fuels. We may not like that in terms of the environment, but they will be around for decades to go. So it's not like this is going to substitute every source of energy we have overnight. You know that, you hear that, you read that in the news, and definitely it's a long way to go. Another things we can make a comment here is about the battery storage solutions. So we don't necessarily connect this with the footprint we have out there. So we see the turbines, we see the solar panels, we see a beautiful landscape in the middle of the nowhere, but that is not functioning alone. So that source of energy, that power, go to battery storage solutions, battery storage units. And they are electrochemicals facilities with all the hazards and risks and profiles and activities that we can anticipate in a facility like that. We will make a comment about that shortly in the next section. Now, what else we have there? Mobility. Well, mobility includes the electric mobility for vehicles, so solutions in which so we provide charging opportunities for vehicles. You may see this in shopping centers. If you go to one shopping center nearby to your house and you see something called Volta, well, that's connected to our solutions for customers in the company I work for. And that is populating, more often these facilities as an opportunity for customers. But there are, other mobility solutions. There are mobility solutions that include the aviation portfolio, include the ships and navigation. So anything that allows to move people with a cleaner energy can be fit there. So it's a large component. We also have the low carbon solutions. What that means? So what that includes energies that are called carbon-free type of energies, like hydrogen, right? So we use electrolysis to produce hydrogen. It's been around for a while. There are vehicles in many countries that function with that, even here in our country. So hydrogen is a well-known source of energy. But what this means for the energy transition is maybe the construction of greenfield huge projects. So examples are in Europe primarily that I can mention here. So large facilities that can substitute the energy consumption, for example, for a huge truck fleet that also is implicated in the transportation of goods and services in a given country. So this is another key source of energy, including in this portfolio. And carbon capture and storage. It doesn't sound like energy directly, but it is a key component here in this landscape. We cannot do that transition without that component. That means take that CO2, capture that, transport that, and bury that somewhere, like in a well, or going to a repository for that carbon to eliminate that contaminant from the atmosphere, and to allow the processes to be cleaner and to be to meet the goals for low carbon emissions that this industry and all the countries are committed to. And renewable gas. I put a cow here. So the cow manure is a key source of energy. One single cow can definitely power a truck for thousands of miles in a year. Wow, this is like, going to the gas station several times during the year with a gigantic gas tank and fill and refill and refill and keep going. So a single cow can power that truck in a way that is based on low carbon solutions like renewable gas, primarily methane, right? And we will talk a little bit more about that process in the risk profile, but count that as well in this portfolio. And finally, one more area that is not so well known, but is also connected to this landscape. It's the nature-based solution. So the ecosystem, the natural ecosystems have a tremendous ability to capture CO2. And this capturing CO2 can balance out the equation of carbon credits. So protecting the environment, looking for projects or solutions in which farming can what is called carbon farming, right? Or work the previous or traditional ways of farming can regenerate land and increase all that ability that the ecosystem have to capture that carbon. So that include replanting, that include farming, that include projects that have to do with forests or areas for farming in general. It doesn't sound, again, like a new energy component, but it is connected, it is integrated to this landscape, and we are not going to get there without combination of assets. So I think that the key message here is that all these renewable projects are connected to decarbonization for the assets that the current industry has, reduction of emissions, and give the ability to customers that are interconnected to these processes to also decarbonize and meet their goals. So chances are that we see a combined strategy that put many of these solutions that we review briefly in these few minutes interconnected or combined. One of the examples we're going to discuss today actually includes a combined strategy for a refinery. And I think that going through that will give us an idea how this really can play an integrated role in the energy transition. So I think that with that landscape in mind, you may visualize how the health and safety risks are located in all these complicated landscape. I think that the important thing here today is to maybe highlight a few things associated with those risks. We are all experts here. We are all working for years in protecting people through the industrial hygiene component of public health. We're not yet in the providing these services We are studying hard to get there, and so I hope this review help us to highlight, pinpoint some critical aspects of the risk profile. Basically, here, using the traditional nomenclature in industrial hygiene for hazards, health hazards, I'm going to start with health hazards and then go through some safety and environmental hazards as well. But here, the chemical hazard, using the nomenclature again, chemical, physical, biological, ergonomics, and psychological hazard. So we can visualize here, a variety of chemical hazard associated primarily with the battery storage units. All these metals are there. Actually, the solar panel have those metals too. And understanding that heavy metals are, a traditional hazard and well-known hazard that have defined monitoring, biomonitoring, or exposure assessment well-known. So we definitely think that we tend to think that these issues are not high in this type of clean industry or clean energy industry. So, and that may have nothing to do necessarily with these heavy metals components, and we really need to map out those and acknowledge those. In the carbon capture and storage component, we have amines and CO2. Let's say a few words about the amines, and that include piperazine, nitrosamines, for example. These are chemicals that are strongly regulated everywhere, right? You check the TLV, the exposure limit for those amines, they are very low. Particularly piperazine is considered a carcinogen. So these amines are part of the carbon capture solutions, carbon capture liquids that are part of the process, is contained, is very well managed. Don't get me wrong. I'm not saying here this is something out of control. It is very well managed in the design, containment processes to reduce the interface with the worker, with the operator during maintenance. There are a bunch of controls there, but we need to acknowledge they are present there. And in some cases, not very often, but can happen, in which the operator and the worker have to do manually certain work or sampling or inspections or be exposed to possibilities of a leak or an emergency. So keeping that in mind is critical to not only evaluate the scenarios, identify how the plume or emissions, if we are talking about a flare and with workers in the proximity, or how this, when it's integrated into an existing facility, let's say a refinery, and there are workers around that have nothing to do with the process of capturing CO2, can be exposed during an event when venting is there, or even thinking about how the community, outside the fence, can be exposed to that in an event of an emergency. Or for the environmental standpoint, if these amines go up in the atmosphere and then go down as a result of air currents or any other factor, and they go to the soil, are they going to really persist in the soil? Are they going to be a contaminant for the soil, that will persist? The quick answer is no, but we need to really be sure whatever technology we use, we are able to identify these hazards, and we are able to effectively assess the controls that are in place there. A key component in that part is the design. And I think that another area in which I would really like to talk to you about is the tremendous opportunities for design input in the HSE arena. Moving to hydrogen and nanofibers, not much to say here, but nanofibers are present in the, as coating material for several energy solutions equipment, including the wind turbines, right? So we have painting and coating and air and also coverage for maintenance that use these materials extensively. We not necessarily visualize that clearly, but it is there, and it's another new hazard that we need to take into consideration. Chemical hazard is a long list. When we're talking about producing a low carbon gas or methane, using, for example, technology that in a digester or technology that have to do with a chemical process. What we call biofuel, few words quickly, is a fuel that is low carbon, and it's more friendly in terms of carbon footprint. But the production of that can be really connected to polycycle aromatic hydrocarbons, exposure to dioxins. It's being measured when we have high temperature processes above several hundreds of Fahrenheit degrees. So you can see those, you can produce those. Now, is that a direct exposure to workers? Maybe not in normal operations, but when in an event of an emergency, in an event of a leak, loss of containment, in an event of maintenance, actually, which is somehow planned, those possibilities exist in the human interface. So we need to also visualize that. Anytime we use organic material in a digester, remember a digester is, put it in a simple way, is a kind of a cow's stomach made of metal tanks and engineering parts, but it's exactly like that. When I was a kid, I was taught in the school that the cow have 4 stomachs. But anyway, let's say you have 1. So anything inside that reach a high temperature, right, go to decompose the organic material. So now translate that to a big tank, tight tank, with a lot of thousands of kilos or pounds of manure, and then microorganisms are going to produce a feast there and produce gases, right? So hydrogen sulfide is there. We are not escaping from that. It's a well-known enemy from the traditional hydrocarbon processes and energy production, but it's also here and very dangerous. The industry have reported a lot of incidents associated with that, and it required not only the measurements, it required the definition of zones. It's an acute toxic substance. Can be fatal above 600 parts per million, can have actually tremendous health effects, loss of consciousness. What I can tell you about that. You know all those components, but it is there, and we don't necessarily confine these to the tanks in I will say a regas facility. They are in the pipelines. They are connected to the inspections interfaces in which samples had to be done, in which the visual inspection the operator had to be performed every day. If we reach there a high concentration of hydrogen sulfide, we want to be sure portable equipment is worn by the workforce, appropriate training, appropriate measures to identify high concentration or safe concentration to escape, for example, protection equipment to protect people, and a procedure that everybody is extremely well aware of that. Unfortunately, as we gain knowledge in the integration of projects, we have seen some gaps, particularly in managing this risk. So that's why it's important that we really mention it and dedicate a few words here to recognize how dangerous is this, and we cannot overlook that part. Catalysts and lubricants, a good example here is that on the right you see a picture of the gearbox inside the turbine. So all those little points need lubricants, and it's an extensive type of work. And, believe it or not, in that small space, there is a worker all the time, doing this maintenance and helping with that. So another component to take into consideration. Finally, anything you can find in a construction site, right? So we're talking about construction here. We're building that wind farm, that solar farm, and we are keeping that site in good shape. We're landscaping, we are managing all the maintenance part, we're keeping the pests out, particularly rodents. And so we use a variety of chemicals there. We are moving terrain, we are moving earth to really prepare the ground for the foundation of these gigantic turbines. They're not so big now. There's probably half of the size that they were before. I would say there was probably something about 100 meters tall in turbine. Nowadays we have some that are half that 50 meters probably have that height. And the things have evolved, but definitely the construction is a big part here as well, because we are building those farms in general. When I say we, I'm not saying necessarily my company, in general, all the companies that are connected to this renewable and energy transition component. Moving to the physical hazards, well, we know that for the physical hazards, we need to recognize something that have emerged as part of the carbon capture and storage component. So the equipment associated with that technology, compression, venting, moving CO2, and doing compression inspection, opening the compressor, is not very often, not daily necessarily in a continuous way, but that proved to be a source of noise, and it's significant. Now you visualize, please, this carbon capture unit in a refinery, for example, or in a chemical plant. And it's one unit that is being built inside the fence. And now you have that moment of the day, I don't know, a couple of times a week, in which you reach about 100 decibels when you are venting or when you are doing something in the compression that require, opening some gates and do some maintenance work. So, and now you visualize, an administrative building not so far from that area, reaching out, that level of exposure, right? So those are new problems that noise in this type of technology deployed inside the fence, or what we call brownfield projects, is bringing. A great opportunity as well to understand how this can be mitigated. Of course, these projects have a balance between solutions for engineering solutions and cost. Nowadays really is so critical that equation is balanced. But an opportunity to add value and protect our people is definitely anticipate this noise control, opportunities in the design, for example, and be able to help the company or the development not only to acquire less noisy equipment. There are some tools that we could use on that, but modeling, for example, is proved to be a very helpful tool for us. Now, industrial hygienists don't do that modeling necessarily in a routine basis. We can hire specialists that can definitely help us in the IH plan to do that modeling. And he also have the advantage that provide valuable data to identify community exposure, which is also important to visualize. And then with those numbers, we can, identify areas in which emphasis had to be put for controls. Can we add here, engineering solutions in advance? Can we, use other other measures such as distance, such as equipment layout, changes in how the equipment is going to face certain areas inside the fence, and most importantly, predict what is the level of exposure, complete a noise map, and and put in place measures even before we start building anything. So that is a great opportunity for industrial hygienists, for the HSE, to definitely add value there. In general, the other hazards here are very well known, and you can definitely connect that vibration with the use of hands tools, and also the whole body vibration is present, particularly in the offshore installations. We have people in those offshore loneliness, and they will be spending time there, and vibration is definitely a risk. We can also identify the thermal stress in those fields, not only onshore but also offshore. Thermal stress, and I include here also the cold surfaces, or the release of very cold gas. CO2, when it's compressed, you are familiar definitely with how a gas really behave for changes of pressure, changes of temperature. So if we are venting CO2, for example, in one of these units, it will come out very cold in certain processes. If we have a release that is above certain level, that is fatal. Some of the more dramatic incidents in the globe that we have seen associated with CO2 release are unfortunately being fatalities, because definitely we cannot breathe that cold gas without dying immediately above certain concentrations. And this is well known, those concentrations. I don't want to really spend time on that, but there are concentrations in which that risk is very high. But even if we don't reach those dramatic concentrations, and we're not talking about here fatalities, chances are that you can have definitely effects due to low temperature and low temperature surfaces that are not quite classify as thermal stress, which is what we experience in the field. Either heat stress or cold stress, equally valid, but it is something associated with the thermal hazards that we definitely need to map out. The ergonomic hazards also. In this picture here, you see this gentleman, using a handheld tool, standing long hours. It's not that it's very easy. It looks pretty. It looks simple. Those farms, but those farms have a lot of work too, and it gotta be many manual things had to be done during construction and inspections of solar farms, for example. There are a lot of walking, standing, lowering, and use of carrying tools that can be identified. Wind turbines also have a lot of ergonomics components, and you have to climb, you have to go up and stay in a narrow space. You need to move yourself, in those narrow space. You have to stand and looking for the variables you are collecting in your inspection, and definitely that is very associated with the ergonomic hazards. For biological hazard, I can tell if we include here the nature-based solutions have to do with farming. All that is applicable to that part is actually in this renewable sector as well. I put a couple of bats there, vampires, because what I have seen a lot in wind farms, is encounters with these little animals, actually, I like I like them. There are protected species in several states here in the United States, but they are looking for a place to stay. They are moving at night. They may be attracted, by these turbines, and sometimes they try to nest there, or if not, they are going to maybe look for to escape from the inclement weather. Whatever happened there, you can find those inside, and then you have this dilemma, right? You have a worker there that is not prepared for dealing with these hazards. There are several bodies there, maybe alive, maybe not so alive. So how can they move those safely and avoid exposure? So it's another area. So we are not really preparing these people to do that. We can even include here a certified contractor that can deal with this biological hazard. How can you dispose this safely? And then if they are alive, it's a risk, right? They're carrying diseases. Rabies is one, but other diseases are present there. If you try to catch one of those little things, little guys, they can bite you. And, all these things will knock your door as an HSE professional. What do I do? Well, let me see. Yeah, it's not something that we definitely are very prepared to do that, to address, but it will come to your house, and definitely something that will grow in extension, since we are having a lot more of these facilities. Psychological hazards, the interfaces with the equipment have changed. In the offshore world, the use of robots to go undersea and inspect structures, drones, right? The control room becomes I would say, more friendly or better for the interface with humans. But all those are new interfaces and are associated with somehow with psychological hazards. You are in a construction project, you are a tight timeline. You need to fulfill a plan, and that includes a lot of pressure, a lot of demands, a lot of long work hours maybe, and that is definitely recognized and a clear as a clear hazard nowadays. Mental health is also in general, an issue in construction projects. So this is not different here in this type of construction projects. Now, when you are building something remotely, that isolation that bring particular challenges, particularly for the emergency response. Working alone, working in this, maybe not in the US, but you can have countries in which lack of infrastructure is a key factor there. So you really, communication are not good. Transportation is a high risk. And so it's another factor there that is impacting the emergency response. Moving to more safety hazard, electrocution is there. Remember, grids and network for distribution to customer is part of the equation. It's part of the equation, not because it's actually in the end what people care about. Where I want to switch the light, and when I want to turn on the light, and this is what counts, right, for the customer. So where is the energy coming from? They may not have a lot of reflection about that, but that includes definitely the grids and the way of bringing that solution to the customers. So the traditional electric hazards associated with these processes are present there. Right, road transport. Let me say that in lack of infrastructure type of environments, particularly overseas, in certain countries, the transportation can include anything. Can include motorcycles, for example, something not necessarily seen in the United States, but in certain developments in Africa. I mean, the motorcycle is the critical transportation. So what we cannot say to them, okay, you cannot use a motorcycle. Now you use I don't know, a BMW electric car to get there and, put those solar panels. Well, we cannot say that. We will kill the opportunity in that market. We're not going to serve that community, bringing the energy they need, and they are really in need in certain countries. So we need to deal with that. We need to manage that and mitigate that as an HSE professional. The road transport assessment is critical as well, and it's coming to us, because it's an integrated approach that needs to be considered here. Road transport mitigation plan includes, for example, emergency response, include fitness to work, which is a kind of a medical aspect here in the equation, but it had to do with is the person really fit to go to a long distance and stay isolated there, and does he has a health overlying condition that will prevent him to safely do that work? Are we going to identify a way of managing this in coordination with industrial hygiene, who is going to provide the health risk assessment of that activities? Maybe the health risk assessment will say, well, we have biological hazard there. We have snakes, we have animals, we have thermal stress as a physical hazard, we have fatigue there. And then the HSE, the safety professional, will identify working at heights. They had to climb, to go to the roof of somewhere and install that panel. That is combined, and it can predict in a scenario that it is associated with emergency response for that transportation as well. So keeping in mind what is the risk profile from the health standpoint will help the safety professional to identify measures to provide appropriate emergency response. Yeah, not only for the traffic accident in general occurring on the way, but also occurring in the site. Yeah, so you see, this is interconnected, and it's a great opportunity to work together as a combined technical authority or expert for health and safety. I put there a picture of a cruise in Galveston, and that is also mobility. Providing clean energy for those vessels to get the electricity they need is definitely unplug them when they are in the harbor or when they are on the deck. It's another strategy to decarbonize customers. But it's also bringing chances for working at heights and other hazards that are safety hazards associated with that activity. Fatigue, we can see fatigue here, not as a necessarily as the physical fatigue, right, as a product of working hard, the muscles. Of course, that component is there. We can see fatigue here more connected to lack of sleep. Let me explain that a little bit. So if you are working intensively and you are spending a lot of hours, many hours in an activity, and definitely this can happen in construction or in projects. So chances are you reduce the time for you to go to bed. Let's say you are working from, 6 a.m. to 6 p.m. So you are investing 2 hours to get there into the site as a worker, as a contractor. Then you spend 2 hours to go back home, wherever home is, typically a camp around or a housing around or a hotel. So it's 8 p.m., you are cooking, you are cleaning, making the bed, whatever, and then you go to sleep at around 10. And then you have to wake up at 4. So you don't have 8 hours to sleep, right? So then this fatigue factor accumulates. This lack of sleep is a debt that is difficult to pay for the worker. And there is where the danger is, right? Is when the dangerous part is when you have accumulated lack of sleep. This is extremely connected to, fatalities in this industry, not only in the traditional hydrocarbon industry, but also, in this industry as well. So anything that mitigates that, for example, reduce transportation time, have, conditions in the housing in which the worker can go to bed earlier because meal is provided, for example, or maintenance to the facility is provided, so they don't need to do that. I know it's difficult. I know who's going to pay for that, right? But, it is a good business, really, to address fatigue. This is a single factor that is really associated with incidents. Not only driving, transportations, road transport type of accidents, also accidents in the operations, accidents during the construction, and any kind of incidents associated with lack of mental focus on the task, right? So definitely a big one to map out. And again, it's in the list of industrial hygiene hazards. It's not necessarily a traditional thing that we manage, right? But it had to be included in the health risk assessment. And finally, for this risk, the community health, right? At the end, when we say environmental health, environmental issues, it's all about health at the end, right? We are in part of that environment. We need clean air, clean water, and we all are servicing from that. So the community health is connected to emissions. What type of emissions? Well, all these metals that we're talking about, for example, lack of containment that can release gas, can release CO2. CO2 is a big concern in transportation through pipelines. The communities actually don't like much, in our experience, see that those pipelines nearby their housing, nearby their school, nearby their hospitals. The communities are very reluctant, to that type of pipelines. It can be a release. It can be actually when, depending on the pressure, the air conditions, the humidity of the environment, a cloud of CO2 can produce a thick cloud or fog that is actually have been reported as a safety hazard in a highway, for example, blocking the visual of the drivers when that happens. So in examples in other regions, not necessarily here in the Americas, but that can be seen. And people also don't want the footprint of the, you're very aware of that, of the turbines and how this is actually plugged into their natural landscape. Farmers are not really so willing to see those developments in their land. So all these have a health impact that requires a lot of stakeholder engagement, a lot of management of community health, and be sure that when we are called to review a community health plan, we identify the health hazards aspects there and the effective and good way to mitigate this. I have a weird feeling that I was talking to myself in the last couple of minutes. Could you tell me you still can see me, can see my slides and hear me well?
Yep, we're here.
Thank you. And you see the slides too. Okay, thank you. That was my paranoia. Okay, good. So we're moving to say, discuss a little bit the emerging, or present to you before discussion, the emerging technology and how they are combined to traditional energy production processes. Now, by marking here in green some of the areas I really see as a great opportunity for us to expand the conversation. And in red, some components more associated with challenges. But in general, the landscape is interesting in terms of this emerging technology. We have technology associated with surveillance and inspections. I'll give you one example. Carbon sequestration or a carbon capture column can have several meters, let's say height, 40 meters, right? you visualize, please, in the top of that column, a platform in which a worker occasionally had to go up and inspect equipment and maybe manipulate, I don't know, equipment there, a valve or something, not complicated, but it requires a human interface there. Now, let's say, you had to go several times a year up and 40 meters. There is a means in the content of that column capturing CO2, right? And then, we're trying to prevent any potential incident when the worker is up there. And it's not the same going there, 50 times a year versus use a camera that most of the time connected to a device that can definitely capture data every day or even several times a day or whenever we send that to capture data, and then ended up being an interface for the worker only twice a year. See, this is a significant reduction of exposure by using this emerging technology for inspection and visualization of integrity of a system. Offshore development is a great example as well, in which this technology can be deployed, and undersea visualization inspection techniques are also proving a value without necessarily exposing the people that much to the environment. So the other interesting technology, and you can see in the bottom of this slide a diagram that illustrates that a little bit, is the direct air capture of CO2. So this technology is being assessed and built and deployed by several companies. This is just soaking air from the atmosphere, trapping the CO2 and putting the air back without CO2. It's a simple thing. We say that simply, but it requires an absorbent. It requires a continuous flow of air to the equipment. Then the CO2 is captured, and then in a uniform way, this absorbent is recyclable and is using continuously inside the equipment, and the air is putting back clean. It doesn't sound like we are going to clean the whole planet with these devices, but it is counting tremendously in the equation. Every single component we are talking about here is part of an equation that at the end will reach the goal. I mean, it's not that we are going to reach that with solar or wind alone, or with carbon capture alone, or building nature-based solutions. Every single thing connected here is a piece in the in the equation, is a factor, and then at the end we hopefully will intend to connect that with decarbonization and reaching the ambitious goal the world has. But that is another one that you will see a lot in the diagram again. So powering the equipment will use then clean energy, right? So you see here a solar or a wind farm can be connected to these devices, can be easily deployed wherever environment is present. You can go to the YouTube solutions that not only my company have, other company have for public domain, so you can see how this works. It's an interesting idea that is emerging, and we also need to map out how this is behaving in terms of HSE hazards. We talked already about carbon capture and how this is integrated. Again, the transportation of CO2 through pipes you will see that more and more, and the digester to produce methane or to produce biogas also require a design selection in which we can definitely make the things safer for the operation. The mantra here is design out the risk is possible, construct safely, and then operate safely, right? So you find out the sweet spot as an HSE professional to add value, protect our people in these three components. That is the message of this presentation, and hopefully we can get there in the discussion and see a little bit more through the examples. This is the first example. And it is how integrated are these processes and what are the challenges and opportunities. Let me define briefly what a brownfield site is. A brownfield site is by definition a site that is being operated in operating conditions. Let's say a refinery, let's say a chemical plant, right? It's been there for a while. Everybody in that facility knows well how to operate their units, right? So they are experts in their processes. They are refining hydrocarbons, for example. They're producing chemicals. So they have units that have their own procedure, the control systems for HSE management, risk management. There are contractors that are well embedded in the process along with the staff. Several companies come to do maintenance. There are turnarounds, all that thing that we are familiar with in a refinery. Now insert in that picture a new unit that it is called carbon capture unit that will be built to help that refinery to decarbonize. Well, we're bringing now a specialized type of process with columns, with absorbents, with CO2 capture chemicals, with piperazine or nitrosamines that were not there in the system before. We're bringing here also technology that required a specialized contractor building this structure. We're talking about what we call EPC, an engineering and procurement construction contractor. And they are, in an island in that refinery, right? Not so quite isolated, but, see the challenges. So you have two levels of operation, two levels of activities, coexisting there or in combination there. Now let's add one more piece. Let's say we want to help that facility to decarbonize further. So we're looking for a clean energy source. So we're building also, or we are going to put in this example, a solar farm, right? With all the implications this has for the community, with all the hazard we already reviewed in the previous slide. Now put everything together. What do you have? You have three sources of exposure for the worker. You had a traditional one associated with the hydrocarbon process. You have a unit that is inserted inside the fence, and then you have this solar farm in the vicinity. Now, they are probably happening at the same time. They had to, find a way to, even though they have independence in the way they manage the risk, they had to, rely on site controls, right? For example, emergency response, emissions controls. So they are expert in the carbon capture component, but are they expert in the traditional hydrocarbons management? I'm talking about the carbon capture and storage, builders or workers that are associated with that project. So the challenge for us here is to really manage this complex interface, because we cannot isolate this. This is happening inside the fence for the refinery in this case. And then there are a lot of, concern from the community health in terms of that solar panel. So you are trapped in the middle of that as part of the experts that are advising this ambitious project. Yeah, so it's not only about contractor health management, it's about the standards they will use, how the controls are here interconnected in a way that we are not really producing extra exposure. I already mentioned the noisy compressors when venting CO2 or for maintenance for that compressor can bring high levels of noise. If this is functioning near an administrative building in that refinery, we're exposing or potentially exposing people that have nothing to do with this unit maintenance or activities. See the picture? So all this is interconnected, and this is the new frontier for the HSE professional in our view, that really require a reflection and a more efficient way of deploy our knowledge. a picture, a formula that didn't work very well is see this in isolation. All right, this is my IH work, I'm not a safety guy, or okay, they will manage the safety hazard. It doesn't work like that. So we really need an approach for HSE risk management that really integrate all the knowledge and possibilities. We really want to keep this under control and add value. Now, if we want to see a little bit more about the challenge and opportunities in connection with the previous part, some of the challenges we already mentioned, that the emergency response challenge, that include all these. Now, if you identify yourself as an industrial hygienist or as a safety professional, you will probably see a component of the emergency response. So the industrial hygiene will identify the risk profile, and that risk profile is a valuable input for the emergency response or for the medical emergency response part of the emergency response. Now, if you identify as a safety professional, you will see other hazards as well that will be critical for the emergency response. How can we do safely medical evacuation? How can we really do a response time? What are the key issues from the health standpoint that we can see in that particular operation that really had to be mapped out in the plan, right? So the combination of that knowledge from the HSE is critical to build that emergency plan and to understand how to mitigate that. Are the workers working in isolation? If something happened, what are the communications systems that we can deploy there? Are they effective? Are these enough to really reach, a safe evacuation? This is a new frontier as well. We definitely don't see that much in our regular work, but in these particular buckets of energy transition, we definitely need to have a seat in that table. Otherwise, we really will lose a tremendous opportunity to really protect our people. Input into design is, for me, the most important part here. So you are talking about wind turbines and maybe select what is the model that really is less, provide less hazards or provide less opportunities to exposure time to health hazard or to safety hazards. So bringing up a quick example that when that can be definitely a very promising area for our HSE professionals. We already talked about the carbon capture, the digesters, and the new the noise reduction technology. Definitely anticipation of that is critical. We don't have necessarily a clear framework. You can have a country, a state, county, and industry standard coexisting there, and then you're thinking to yourself, okay, what is the one that really will prevail and I need to follow? There are noise, let's say, regulation in a county that may be different from what a state consider, maybe different, but what we have really know in OSHA in the States, and the industry is saying something else. So how can we address that component and definitely help our business to, reach that compliance in this complexity arena? We also have opportunities to standardize this part in the energy sector. So I bring in here some examples of IPECA and IOGPs, the International Gas Organization for Producers, and these include energy, the energy sector in general. The guidance here is high level. That is what we call industry standards. So you are dealing with different companies in a development, and then you have, your company standards, but you also have, some contractors that, they are not going to be able to follow your standards in the company. Well, you can definitely call this industry standard, and you can say, well, these standards are acceptable, and we want this level of quality, and we don't want gaps in protecting our people. So this made the conversation easier in this complexity, because you can always call these international standards and everybody apply to that. If you are building something, there are workers' welfare principles that are endorsed by the most important companies associated with construction. So that really reduces the exposure to, unhealthy conditions in the workplace. So I invite you to go through these principles and see how that can help in your dialogue to demand better conditions in the project and work with contractors or different interfaces to really put everything in the same page and do the right thing. A little bit of that also can be reachable online, and you maybe the company you're representing is or the university in this case, they can get this standard for free. Not saying this is for free, but most of the time they have no cost, and be familiar with that really help. Data management is one of the tools have been for a while in our sector. So the assessment tool, the new sensor technology allowed us to really build data, big data in exposure assessment. So use that data when available, and that is really will pay off in terms of identify interfaces, exposure, and add value. And with this slide, I will finish. Ready for the discussion, and I think that we still have a few minutes. So this is an example for design selection. So if you typically in the traditional world, so we already the design is set, and we are called as an HSE professional to identify hazards and controls, mitigations, and be sure you have a plan to control those hazards. And those plans are effective when we are going to operate that, right? Now, the new frontier here is to be called early in the game and definitely provide input in the anticipation part. So that is in alignment with our hierarchy of controls of elimination and substitution, because that opportunity is unique. For example, you are involved in the design selection for wind turbines. You are quoting different designs for your project as a company. So there will be several companies, many maybe, sending an option, so you can choose, right? So the selection definitely have engineering specifications and what is the output you want from that project and what do you need, right? That is not negotiable. That is what the company is looking for. Now, there are chances in which you can, provide input as an HSE professional in the selection of those designs. In the future, you can even be able to influence the design as a professional. We're not there yet in this industry, but providing input into selection really is helpful, because, okay, if all the conditions are standardized and whatever you choose here fulfill as a company your goals, your costs, your output, what is your ultimate goal to provide energy here, then there are differences here. So you can see here differences in the type of design. And then we can say, well, what of this design is more friendly for a medical evacuation? What of this design is less associated with vibration or noise? What of this design reduce the exposure to ergonomic hazards? Are these designs be able to be closer to the shore so you have less exposure to the transportation part? So these are the things I'm talking about, right? So we can say internally here in an experience we have, I mean, you are prepared with all the components of HSE, not only the health hazards, but also the safety hazards and the emergency response.
A veces que vieron es mi doble. A veces mando mi doble para que se encuentre con los clientes, pero no.
Sorry. Is that a question? Nope. Okay, sorry. Continue then. Yeah, so you can provide input there, and the message here is when you provide that input and you are really anticipating the risk component. Now, other examples can be, in other areas such as the carbon capture units as well. So we say the design is a great opportunity to really reduce that noise and get out. Wow, we have decades trying to manage that noise. We still have noise in our industry. That's unthinkable. There's no really justification for that. We have the technology, we have the knowledge, but we're still seeing those high level of noise. And it's unthinkable. And the government, the OSHA is really keen to supervise this further and to be sure we can definitely, provide solutions to this problem. The digesters and the biogas production also have great opportunities to reduce risk. And we're not talking about only the human factor aspect of which is associated with health, right? With HSE, the human factor engineering, in which reviewing the design and providing a safer design is their key aspect, right? But we can work with them in that and then add the industrial hygiene component and the safety component to that design selection. Of course, when we are really building a relationship, we have a seat in that table and we have the trust from the project engineers, the project team, to really add value there. How can we get there? Well, business partnering is the key. If we are only wearing the hat of a knowledgeable SME that is very concerned about compliance and law, we may have some traction, but not the whole traction. So we really need also to wear the hat of a business partner, that we understand the nuances of this business. How can we balance the costs and the mitigation components and the effectiveness? We also need to wear another hat here, which is, the hat of, being able to broker or build or bring other professionals that can help us to really have a very strong case for design selection. And that is how can we win in this arena. But it's very promising. And is again very, very connected to the mantra design out, construct safely, and operate safer as well. With this, I think that, Serena, I open here for question or discussion. This is my last slide. I'm going to keep sharing if that is okay, but I will bring then the video. I haven't seen anything in the chat, won't be able to, but
Thank you, Dr. Sanchez. So yes, we have a few minutes for any questions.
Sounds good. Thank you.
I guess I could ask, this is Bill Young. As far as I recently ended up with a project concerning electromagnetic fields, and it seems like I didn't really see it commented in your processes and things like that. Are there any concerns, or there's really not been, the evaluations have shown that the effects are pretty negative on people?
Thank you. Good point. We mentioned it in the slide, but didn't really, you're right, didn't really make a comment on that. I mean, it's been recognized, not really a big source of concern. It's more a community concern associated with the, high voltage lines. We have seen that as part of the community concerns a lot more. We are not really prioritizing on measuring those. We are using a lot of data available to really take decisions. Inside the fence, you can see that as well. Any of these equipment and power generation equipment is associated with this. We are relying more on analyzing data and research out there, rather than internally undertaking new measurements. But these things can change as as we evolve or definitely integrate more and more units. This is bringing a lot more attention. But internally in our projects, we have seen more in the development of grids and high voltage structures associated with community interaction. And this is definitely a good point that it's been around. It's difficult to find also an exposure limit at work. I mean, working with the World Health Organization and with other sources of data, we can find some different levels of exposure assessment and limits.
Very true. Thank you.
Welcome.
Okay, welcome back, everyone. We will get started with our second presentation. As I stated at the very beginning, Jan Cohen has graciously accepted to present in the place of Jeremy Schaub, who had to withdraw because of a family emergency. So I know Jan is very familiar to many of you. So Jan, if you could just also give a brief introduction of who you are to people who haven't met you yet.
Okay, my name is Jan Kane, and I do industrial hygiene consulting through my company, JK Incorporated. I'm also doing this as part of Continuing Education Director for Gulf Coast AIHA. So we've been partnering with Serena and the Southwest Group through this IH speaker series to help get some CE for our local section. And so that's another reason for, keeping up the webinar and making sure we have speakers, because I know we're all moving towards documenting the appropriate CM points as we continue our certifications and also do great networking among our members of the local section. All right, so I loved Marcus's presentation. I love exposure assessment and looking at hazards, and I think it's real interesting the way he categorized and put out, chemical, biological, physiological, ergonomic, or psychological, ergonomic, a lot of those types of things. So I have to take a somewhat traditional industrial hygiene approach and look at indoor air quality, but I wanted to kind of broaden it, and I found some stuff to kind of reallocate and use. So I'll probably bounce between indoor air quality and air pollution, because he's going to be doing stuff out on construction sites, maybe not immediately next to residential or office building type environments. So when I talk about indoor air quality, I'm probably looking that way. But I also wanted to key a little bit more on the ambient stuff. All right, let's jump in. You ready, Sylvia?
Yes, I'm ready.
Okay. Next slide. All right. So I pulled in a little bit of stuff from NIOSH. When we do exposure assessment or look at health hazard evaluations, we're looking at a lot of stuff that is published by NIOSH. Among various industries and occupations is listed on this slide. And this one for renewables or energy is certainly going to be a little bit new box to check and look at, but we're going to be looking at hazards and exposures from chemical, biological agents, things out in the field, as well as our standard physical hazards and the ergonomics as well. So we're looking at a little bit different diseases and injuries. All right, next slide. So from an indoor air quality perspective, NIOSH has published quite a bit of stuff on indoor air quality, which I consider more in buildings. Also, we see some of that in the residential environment, even though I don't do a whole lot of looking at that, doing assessments within that environment. But a lot of the things they published from these health hazard evaluations has been regarding mold and microbial agents, which I'm going to touch on a little, not much, as well as other types of hazardous materials, lead and asbestos, and some of these are referenced here. Next. All right, so indoor air pollution. We usually look at chemical and biological agents as our first group or categories of hazards. This is a little bit older information. This is referencing over 900 compounds in 1992. You certainly know there's way many more than that in these days and times. And usually indoor air quality in buildings and facilities is looked at from adverse health effects in closed indoor environments. So we're going to have to look how things get entrained into that environment, how it is being distributed through mechanical ventilation systems, as well as maybe being infiltrated into the building. We as industrial hygiene and safety guys want to look at the dose, the rate, the concentration, but we're also going to look at basic indoor air quality parameters related to temperature and humidity. So we're going to look a little bit at the outside air, because hopefully we're taking some of that in, mixing that with our recirculated air, not so much in homes or residences, but in public and commercial buildings. Next. This one touches a little bit on the biological, even though we're not going to necessarily dwell on that. So there are many different sources of pollutants. Here it talks about bacteria, mold, mildew, animal dander, house dust, mites, pollens that come from plants, and other types of proteins. Things can get entrained into the air handling system, and therefore they can be moved about. They can be diluted in some cases, as well as moved about to other areas of the facility or the residence. Next. All right, indoor air has been known to contain higher concentrations of pollutants. We're taking it from the outside ambient environment, getting it into an indoor building, and in some cases, they've shown concentrations up to 70% greater. There's a whole lot of more synthetic materials now that are out there that are being used as fabrics and finishes, both in workplace environments as well as in residential and other occupied public and commercial buildings. These buildings are enclosed, so we're using mechanical ventilation systems to reduce the heat loss and improve the energy efficiency. In a lot of cases, the energy efficiency has closed up buildings, brought in less outside air, recirculated more of internal air. So therefore, that could as well contribute to increasing the amount of pollutants. In some cases, the ventilation systems are sealed off. Again, we get into that recirculation mode. Windows don't open, and many of the buildings that we've built recently and probably will continue in the future. And therefore, these pollutants can become trapped inside the buildings. Next. Indoor air pollution is usually a greater threat to human health than the outdoor population. In the outdoors, it's ambient. It could be a little more dilute, whereas inside, in some cases, people spend more than 90% of their time indoors. And so there can be greater exposure and potentially greater impact. We certainly have to look at traffic in the urban environment, especially here in Houston. 18 times higher is the general relative comparison between the indoor and outdoor environment, and associated with that traffic patterns and stuff and commuting. Next. A whole litany of hazards can be listed with respect to indoor air quality in buildings and other types of facilities. I start out with a little bit of a short list regarding the microbial agents, mold, bacteria, other infectious agents, allergens, fungi, and yeast. We certainly spend a lot of time looking at that in the hospital. We do a lot of infection control and a lot of air monitoring and bioaerosols associated with opening new patient care areas, etc. We have to think about asbestos and lead, depending on the age of the building and the facility. May not necessarily immediately become airborne, but there could be a potential source or reservoir associated with that. We also have radon listed. Bill mentioned something about EMF, and he may have some other input into that. He did some pretty interesting projects. I've done monitoring on one or two things out on EMF, and I don't have a really burning understanding of all of that. We have to think about formaldehyde that can be off-gassing from different furnishings or other types of manufactured processes. So that could be available as a contaminant within facilities. Volatile organic compounds, maybe hydrocarbon compounds that we can recognize and identify, or other screening with instruments with the PID, and just looking at general volatile organic compounds as a grouping. Pesticides, perhaps there's been some type of application in those environments. Particulate, huge wide open category. Are we talking about ultrafine types of things versus more medium-sized particulates or larger? Maybe we're looking at particulate matter, 2.5. The size has become much more important than the PM5 or PM10 that we initially started to look at when this started to be an impact within the workplace. Products of combustion, as well as there are basic indicators that we look at for indoor air quality when we do monitoring, and we always do monitoring inside as well as outside facilities as a relative comparison. Next. This is a table that I obtained from some EPA information. Just gives you a little bit of a laundry list of different types of pollutants. Again, some of these you may see in the outdoor ambient environment, the trichloroethane, the benzopyrene from tobacco smoke, again, those combustion products that we just mentioned, carbon monoxide as well. Next. Chloroform, formaldehyde that I mentioned is a carcinogen, off-gassing from paneling, particle board, methylene chloride from paint strippers, nitrogen oxide also is a combustion product. Next. Radon, okay, coming out of the ground, styrene from carpets and plastics, other types of organic organisms. Some of these may be microbial related, some of them could be chemical. Next. So other types of pollutants, again, some of these combustion products we just mentioned at the top on the left-hand side, also some of the microbial, dust mites, allergens, mold or mildew, asbestos and man-made fibers, maybe also lead. I didn't add it to this list because it was on the previous list. And sources of these within our interior environment could come from building materials, different types of furnishings and fabrics, glues, cleaning products, again, our combustion products, off-gassing from heating, as well as cooking, open fires, probably not having that in the indoor environment, but available in the ambient. Smoking, again, off-gassing some of the chemicals as part of that combustion, other types of microbial agents, and hopefully we're taking in and diluting and mixing with some outdoor air, but that's a little bit more limited in the residential environment. Next. All right, so just a picture to show. I don't have many pictures. So how can things get in? How can things get out? What are some of these sources that could potentially be associated with the residential environment? Old types of paints could be the lead, fireplaces and stoves, unvented stoves and heaters are going to give off some of those combustion products. Animal dander, allergies, health risk associated with pets, pesticides, paints, and cleaning fluids, tobacco smoke also, gasoline from the vehicle, even though I guess we're moving more towards hybrid and the renewables as Marcus touched on, furnitures, carpets, foam insulation, and heating and cooling ducts. Again, a variety of sources, could be a contributor, could not, but we have to think about that as a pretty complicated interior environment. Next. Again, different sources, the gas stoves, gas heaters, and kerosene heaters. Again, off-gassing from combustion, from hydrocarbon types of fuels, the kerosene, natural gas, car exhaust from the garage. How is the garage connected to the residence? What are the air pathways that may connect between those two? Could become a point of entrainment. Next. Others could be interior to the residence or the building. Particle board, plywood, those are going to be off-gassing some of these products, the paneling, and then if we've applied some varnish or used some solvent or have other types of pet products that could potentially be involved. Next. So sick building syndrome, we're going to talk about sick building syndrome as well as building-related illness. This is a sickness produced by indoor pollution, and it may have a variety of general as well as non-specific symptoms. Some of those could include dizziness, headaches, coughing, sneezing, nausea, burning eyes, irritation of upper respiratory. It could be a persistent set of symptoms in greater than 20% of the population. And there can be complaints or symptoms, perhaps for more sensitive individuals, but usually they're reporting when they leave the building or outside of the facility. They get pretty immediate relief associated with that, come back the next day, and some of it kind of starts all over again. Some of these causes are not necessarily known or recognizable. The newer buildings may have more common impact than older ones because usually these are a little bit tighter. There's not more infiltration taken in, a lot of outside air is leaking in because they're pretty tight along the seams and all the intersections and the way the mechanical ventilation system is operating. And hopefully we've used lower toxicity building materials and have a good ventilation system that's well balanced regarding what's being recirculated, what's being brought in, how it distributes from point A to point B. Next. Building-related illness. These are also related to exposure with indoor air pollutants. Some of them have recognizable causes, even though it's pretty hard to link exposure and disease and symptoms one-on-one directly. Some of the clinically recognized disease that have been associated with building-related illness are the Pontiac fever, Legionella back in the old days from the cooling towers that got entrained into the indoor air intakes for buildings, hospital, Legionnaire's disease, hypersensitive pneumonitis, asthma, allergy, or different types of respiratory diseases can show an impact on the human body. Next. Living organisms. I said not to talk too much about microbial agents or mold, but we can talk about living things that are different to look at or sample as different from chemicals. These could be dust mites that feed on human skin and dust. They can live in different types of materials that will help promote the growth, bedding, and furniture fabrics. They can cause asthma attacks and allergic reactions, again, in more sensitive individuals. We live on the Gulf Coast, so we're pretty much surrounded by fungi, mold, airborne agents, mildew, etc. So again, depending on the sensitivity of different individuals, could result in illness processes associated with allergies or asthma or impact on the respiratory system. And animal dander in some cases can aggravate asthma. Next. I did find one picture that had some interesting things regarding the dust mites and the pet dander. Have no idea if they really look this way, but we need some visuals in some cases. So here we go. Next. All right, so indoor air pollution in the developed world. According to EPA, they listed 4 of the most dangerous indoor air pollutants in developed countries, and they listed them as radon, formaldehyde, tobacco smoke, and they just had particles. I expanded this a little bit to talk about ultrafine particles, and we certainly have been looking at, from an exposure assessment standpoint, nanomaterials, how to safely handle those, how to provide appropriate protection for personnel that are working on them in the research and development world. And I had to throw in my other considerations, asbestos and lead, as well as total volatile organic compounds and or pesticides. Next. All right, let's talk about each of these a little bit. What they are, a little bit of the health effects, and maybe things that we can help from an exposure reduction perspective. So radon, colorless, tasteless, odorless radioactive gas coming from uranium, usually in the ground, and can seep into houses. 55% of the exposure to radiation may come from radon and may cause long-term exposure, can increase the risk of lung cancer, and especially can be a synergistic effect related to if you're a smoker or not. Causes greater than 20,000 deaths annually in the U.S. This is probably some older numbers that are associated with these statistics. There are some options for reducing the risk associated with airborne exposure, sealing cracks in the floors and walls. This is more related to residences, or putting in a type of ventilation system, an exhaust system that's pulling that out and getting that out of the internal facility. Next. All right, just a picture regarding how radon can enter the house. From the bedrock, from fractured bedrock, perhaps through the soil, getting in the water well, and then that water is brought into the house as a source, getting in through groundwater, maybe coming up through the lower levels into the sump, through windows, through cracks, and other types of drains and things associated with the water table. All right, next. Health effects of radon can be related to elevated levels of lung cancer. We showed it as a groundwater pathway with water intake, so coming out of the shower, taking in water, breathing air contaminated with radon. Many different health organizations like the CDC, the American Lung Association, and AMA agreed that it could be related to lung cancer deaths. So this is a preventable point that we could be taking a look at. Estimates about 14,000 deaths per year in the U.S. related to radon, so pretty decent high number. Radon and smoking, again, is that synergistic effect, also works to increase the risk of lung cancer. Next. How can we reduce it? All right, so we're usually looking at, it's estimated to be 1.3 picocuries per liter, whereas outside in the ambient environment, we're usually seeing 0.4 picocuries per liter. Home repairs for radon levels are usually kicked into gear at a level of 4 picocuries per liter, and most homes, through using some of these options that we alluded to, can be reduced to 2 picocuries per liter. It still poses a risk less than 4, but these exposures and potential health effects can be reduced if you get it lower than those levels. Again, our options are dealing with sealing cracks and other types of openings in the foundation, or installing systems with the vent pipe or fans from the crawl space to be able to pull that, exhaust that out, and get that out of the airborne environment of a residence. Next. Formaldehyde. Okay, an important chemical used in the building material and household products industry to manufacture a lot of these components. It is also a byproduct of combustion and other natural processes. It is present both in the ambient outdoor as well as the indoor environment, and especially if you're using it in laboratories or other types of settings for testing, it is going to be another potential exposure assessment product to take a look at. The sources in the home could include building materials, smoking, other household products, as well as use of unvented or fuel burning appliances. So this is back to our gas stoves and kerosene heaters. Formaldehyde by itself in combination with other chemicals is usually related to the presence of some of these manufactured products. Okay, so some of the foam, some of the other finishes that could be available in different types of buildings. Next. Health effects of formaldehyde: colorless, pungent smelling, so we're usually picking it up by that odor, can cause upper respiratory and irritation of the eyes, a burning sensation in the eyes and the throat, could be related to nausea and difficulty breathing, so respiratory effects impacting the lung, if you have exposures or airborne concentration at elevated levels. And we're using examples of this above 0.1 parts per million. So not very doggone much, but it does have good warning properties that you can pick it up in the environment. Higher concentrations above this can trigger asthma attacks. Again, different people have different sensitivities. Some can develop a greater sensitivity to formaldehyde, but it has also been shown to cause cancer in animals and or in humans. I think it's been classified in some of the IARC stuff. Next slide. Exposure reduction. Understand that it is part of pressed wood products, other building materials, cabinets, furniture. So maybe look at some of the specs, what it's made of before we're purchasing that and including that in our interior environments. Some that have been treated with polyurethane have been shown to perhaps reduce formaldehyde emissions. The rate at which formaldehyde is released can be accelerated by heat, so higher temperatures, and can also depend on the humidity level, both two things that we usually have challenges with down in this neck of the woods. Use of dehumidifiers and air conditioning can help control that humidity and temperature and maybe potentially reduce some of those airborne emissions. So related to ventilation, you see the exhaust with the radon. You also see that with ventilation of the formaldehyde for interior environments. And if you're using some of this stuff with research and development in laboratories, doing it in chemical fume hoods, to having the appropriate exhaust ventilation available. Next. Tobacco smoke. Indoor pollutants, secondhand smoke from cigarettes. Some numbers have shown 17% of lung cancers could be related to exposures of non-smokers. Tobacco smoke itself has a whole range of different type of off-gassing chemical components caused by the burning or the combustion. In some cases, some over 4,000, probably even more than that, have been checked out recently. Causes eye, nose, and throat irritation, but they do mention that smoking has declined in developed nations. Next. So combustion sources, kind of going hand in hand with this tobacco smoke. Unvetted kerosene, space heaters, fireplaces. The major pollutants associated with these are carbon monoxide, nitrogen dioxide, and back to our particulates. Okay, usually very fine, small, ultra-fine particulates that you're not seeing with the human eye, but can become airborne and therefore an exposure hazard. The unvetted kerosene heaters can also generate some acid aerosol, so a different source of exposure associated with use of those. Combustion gases and particles from chimneys and flues that maybe are not have been improperly installed or not maintained, or have some cracks in there that can allow some of that to get inside the facilities. Next. Backdrafting, all right, if we're talking about residences or buildings, we have heater systems, air conditioning systems, we're venting our dryer, we have exhaust coming out of our restrooms. So a lot of this air is exhausted, and leaks or infiltration can be brought into the facility. Some of that can be replaced by outdoor air, but depending on where the intake and the exhaust pathways are, some of the spaces can become depressurized. If that's the case, then we are bringing in stuff from the outside ambient environment. It can be pulled back down a chimney or a gas water heater, and therefore some of these combustion products and other substances can get back within the facility. So back to our carbon monoxide, particulates that may result by incomplete combustion, and that could create a relatively dangerous exposure situation. Next. Exposure reduction. Okay, obviously pay attention when we're doing some fuel burning or we're using some of these space heaters or furnace operation, how the air is being brought in as well as how it's being exhausted, making sure there's not exterior infiltration, no depressurization going on. A yellow tip flame is usually indicative of improper adjustment, and therefore you may have a little increased, greater level of pollutant emissions. Make sure we're using exhaust fans over cooking stove and ranges, and make sure it's properly adjusted so we're getting the right burning and not an increased level of combustion sources. Take a look at the central air handling systems, mechanical ventilation systems, and the different components of that, and have those appropriately investigated, furnaces, flues, chimneys, and if issues show up, definitely want to move towards prompt repairs. Next. Asbestos, a mineral fiber used in a lot of building construction materials, also present in different types of insulation, and present also as a fire retardant or a fire barrier. Most commonly found in older buildings associated with furnace, thermal system insulation, asbestos shingles on the roof, or different types of exterior wall board, different types of coating, and floor tiles and mastic in some cases. Elevated concentrations of airborne asbestos can occur, but that is usually related to disturbance. So if we're removing a floor or tearing out a wall or doing some type of cutting and sanding, most of cities, municipalities all have requirements now for doing asbestos surveys prior to renovation or disturbance, and that has to be documented and put in as part of the permit so that they can make sure that this has been looked at, and if abatement has to be done on the front end, that it can be appropriately addressed before you turn in a general contractor loose without doing HAZCOM and letting them know exactly what's involved. If you do improper removal, or if you don't know it's there and start tearing up the floor, and we have black mastic and old floor tiles that are becoming friable, then we can have increased levels, and that could result in potential exposure. All right, next. Different types of asbestos: chrysotile, amosite, and croxidolite. The fibers are very small. If they become airborne, you're not necessarily going to see those with the unaided human eye. Chrysotile is called a white asbestos, even though it's not really going to necessarily look pure white when you take a look at it. Amosite is a brown asbestos. That is mined from South Africa. That is used in a lot of boiler, thermal system insulation applications. Croxidolite is nicknamed a blue asbestos. Again, this is in some glittery ceilings and some textured ceilings, more for decorative, not necessarily for insulation purposes. Next. Health effects. Again, small fibers that you're not going to see can become disturbed and therefore be taken into the respiratory system of humans, can impact lung tissue, can form nodules and growth. Your body will try to combat that from some of the defense mechanisms already in place. But the most common disease processes are asbestosis and irreversible scarring. This is back in the old days when we had high dose exposure in the railroad and the shipbuilding industry, usually associated with insulation. Lung cancer is caused by other things besides asbestos, but can be related to asbestos exposure. And mesothelioma, a very, very nasty disease, a cancer of the chest and between the chest and abdominal cavities when you're breathing in and out. If you get some fibers in there, your body will try to build, again, a fibrous nodule around it to prevent it from causing further damage to the lung tissue, but it helps obstruct breathing. Usually when mesothelioma is diagnosed, usually it's pretty fatal within a year or two. Okay, so there has been some type of previous exposure associated with asbestos. The symptoms of disease, in some cases, the latency period for all these diseases is anywhere between 10 and 40 years. So again, trying to backtrack, where were your workplaces? What were your potential points of exposure? The symptoms of disease are not usually apparent till quite some time after that exposure, and also different individuals and different sensitivities. Next. No disturbance. That's going to be the way that we're going to reduce our exposure. Materials in good condition are not going to release fibers. If we're breaking up floor tiles or if we're beating down sheetrock and the tape and float materials, we're potentially releasing them into the airborne environment. And therefore, personnel can inhale them and you can have an impact on the respiratory system. Don't cut, rip, sand, or other types of disturbance that make it airborne and therefore could increase human exposure. Next. Organic chemicals, again, widely used in ingredients in household products as well as out in the airborne environment. Paints, carpet cleaners, varnishes, different types of solvents that we may be using for disinfectant. I know we've gotten to more environmental friendly types of compounds. Fuels consist of organic compounds, okay, and other products can be released from these doing use and storage. Next. Volatile organic compounds obviously means it's off-gassing, it's getting into the airborne environment, and therefore we could be breathing that into the human respiratory system. Most diverse group of indoor pollutants can be off-gassed from materials like plastic, paints, perfumes. Formaldehyde coming off of the pressed wood can cause irritation to mucous membranes. Pesticides, outdoors as well as indoors. Most VOCs are released in relatively small amounts, but depending on the sensitivity of individuals, frequency and duration of exposure, concentration, it can cause health effects or illness. Next. Health effects, again, high toxicity to no known effects, so the whole range from small to large. The extent and the nature will depend on various factors: the dose, the concentration, the frequency, and the length of time the exposure that occurs. Some of the effects could be eye and respiratory tract irritation, headaches, dizziness. Other organic compounds are known to cause cancer in animals, and or some as well has been related to cancer in humans. Next. How can we reduce that? Follow label instructions, avoiding the interaction or exposure from single substances, as well as mixing substances together, especially if they're incompatible, because they can cause other exposures of mixtures. Most of these hazardous products have warnings associated with them. Get rid of unneeded containers and things that you don't need, and therefore lessen that exposure pathway. Next. Pesticides used in and around the home and other types of facilities, disinfectant, insecticides, fungicide, can come in different forms: aerosols, powder, liquids, sticks, foggers. Again, we're having airborne potential exposure points associated with that. Next. Health effects, both the active ingredients as well as other inert ingredients as organic compounds, could be related to exposures from misapplications, headaches, dizziness, weakness, tingling sensations, and nausea. Could result in long-term damage to liver as well as central nervous system and potential increase of cancer. Next. Exposure reduction. Read the labels. Ventilate the area. Have some exhaust ventilation. Dilution. Use non-chemical methods of pest control. Use them. Dispose of unwanted pesticides safely and maintain exposure to a minimum. And look at the personal protective equipment required for safe handling and also work practices. Next. Lead. Previously used in paint, gasoline, some of our other hydrocarbons, and lead pipes. Old lead-based paint can be a significant source of exposure on windowsills or door frames, both inside as well as outside of facilities. Harmful exposures can occur from improper removal of things that are suspect and haven't been tested or investigated. High amounts of lead particles can also result from outdoor sources, contaminated soil, if there's been some inappropriate disposal, or certain indoor activities such as soldering, where you're causing a fume and therefore an aerosol exposure. Next. Health effects could practically impact all systems of the human body. At high levels of exposure, convulsion, coma, even death. Lower levels can affect the brain, central nervous system, blood cells, and kidneys. Fetuses, infants, and children are much more vulnerable since they're growing and expanding bodies, and therefore they are more sensitive to the damaging effects of lead. Some of these have been reported in the literature, and I think we're trying to drive down those exposure limits, both action level as well as PEL and the blood lead level. Lower IQ levels, delays in development, shorter attention span, increases in behavioral problems. Next. So how can we do exposure reduction? Avoid the use, obviously. Do surveys and figure out if it is associated with different residential environments or interior or exterior of buildings. Paint on window frame, exterior or other sources. Not disturbing it if it is in good condition. We can put some encapsulant on it in some cases, but one time it's starting to peel off, they're usually going to have issues with that. Don't bring lead dust into the home. Change clothing at work and wash contaminated clothing separately from bringing it back to the residential environment. We also do testing for lead in drinking water. Okay, and most public water does not contain lead, but if it's transported through piping, then there could be a contamination potential there. Next. All right, the developed world, sick building syndrome versus building-related illness. All right, so sick building syndrome is a term that refers to unrelated symptoms or health effects that are reported by occupants within a certain type of facility. They're usually not easily traced to, oh, this is exactly where it's coming from, or this is the source. And when they exit the facility, usually the symptoms diminish. Building-related illness is also associated with exposure to indoor air pollutants, which in some cases can have identified causes and maybe even specifically linked with a recognized disease. Next. All right, so the sources of the sick building syndrome are elusive, but the symptoms of the building-related illness in some cases can be categorized, and sometimes it's not easily linkable, as I mentioned. So we're looking at a wide range of complaints from minor, maybe irritation, to even some more extreme. Again, depends on the individual, depends on the sensitivity and the response. Next. Pontiac fever. This one is associated with a bacteria. So Legionella bacteria, it's a non-pneumonia type of illness, but can be a high rate of infection for exposed individuals. Legionnaire's disease, also caused by Legionella, but a specific type, Legionella pneumophila. It came out in the 1980s, again, with the cooling tower in the hotel and re-entraining some of that airflow. We also have to think about indoor molds, bacteria, dust, and other chemicals that can result in impact to the respiratory system, pneumonitis and bronchitis. Next. While there's no clear consensus regarding what is related to building-related illness or what is related to SBS, we have to think about this regarding different types of disease process or illnesses. Again, probably a little bit older statistics, but in some cases it was reported the direct medical costs could be over $1 billion a year associated with building-related illness in a variety of facilities. Next. Indoor air quality can also be impacted by off-gassing from equipment, furnishings, and result in additional cleaning and repair costs. We certainly see this from the flooding environment, and microbials are popping up if we don't have temperature and humidity control. But the most significant cost associated with sick building syndrome could be to human productivity. When people come down with disease and illness processes, aren't going to work, aren't being able to help out with workplace environments, that's where we're going to see the impact of this regarding the SBS. Illnesses resulting from pollution can account for over $4.7 billion in lost wages and decrease in productivity. Again, older numbers, but gives you some idea of the type of range or impact. Next. 3 reasons why we look at indoor air quality in different types of facilities and office buildings, because we could have some of these indoor air pollution sources hanging around. We're definitely going to look at the mechanical ventilation systems to see if that is a contributor, or is that a source, or is it helping move it from one side of the building to the other? Is it bringing it in from outside? Are we doing some type of recirculation? And maybe we're using buildings for things they weren't necessarily designed or planned for. We're turning an office into a lab, or we're turning a lab into an office, or vice versa, or shops, and we're using different types of organic chemicals or materials in there, and it's getting entrained in the system and distributed elsewhere. Next. The leading cause of the sick building syndrome is these poorly designed, maintained, or maybe they're not at optimal operation of the ventilation systems. So these are used in large buildings to heat and cool the air, also bringing in outside air, recirculated air, mixing those together, filtering it, cooling it, and sending it back out to our occupied tenant personnel. In different types of workplaces. So problems arise when the ventilation systems don't bring in enough outdoor air. And if there's adequate ventilation, if it's not distributed properly also, it's going to be an issue. Where does your supply go? How does your return get back to the unit? Is it filtered? Is it cooled? How often is the filter changed? What is the PM for that unit? Is there disinfectants or thing in the drip pans to try to prevent microbial growth? So just look at the overall health of the system, how it's maintained, how it's operating, and that's going to be a potential issue regarding the ventilation and indoor air quality. Next. All right, so they can be circulated from one portion of the building for the other. And then if we have furnaces and we have other types of heat sources, we mentioned entrainment of automobile exhaust from either underground garages or from loading docks or from elevator shafts or stairwells that can take it up and down in the building. Boiler emissions, for example, again, buildings designed for one purpose can be converted, and maybe we haven't thought all the way through that process and looked for other pathways where things are connecting or how that mechanical system is operating. Next. All right, if not properly modified, if you're changing partitions or walls and looking at where the supply and exhaust is going on in different types of rooms and the ventilation pattern, it can be a potential source for indoor air pollutants, both for the biological contaminants. We mentioned the Legionella associated with the cooling towers and aerosols coming off of that being entrained into the HVAC system. Next. All right, indoor workplace standards, okay? I keep talking about indoor air quality in buildings, so I'm probably going to look at some of the OSHA or occupational exposure limits, okay? But if we're talking about the ambient, we're going to look at national ambient air quality standards. There's a couple of those, and those are applying to outdoor pollution. But if we're bringing outdoor air into our indoor environment, that could be a potential source. So there are no specific regulations that control indoor residents at this point in time. Again, we're looking at OSHA, NIOSH, and some of the OEL stuff. I'm real close to sure y'all are all aware of PEL set by OSHA and the NIOSH RELs or recommended exposure limits, maximum allowable concentrations over an 8-hour day, which is what OSHA is considering a normal workplace. Time-weighted averages, we definitely look at for PELs as well as TLVs. A time-weighted average for these over an 8-hour workplace period. There are different shifts. There are different contributors to that. The ACGAH is published yearly, whereas the OSHA has been set for some time, but those are related to manufacturing workplaces and do have the force of law. Next slide. All right, so comparison of outdoor and indoor standards. So I have the National Air Quality Standards on the right-hand side for carbon monoxide, nitrogen dioxide, and ozone. These are smaller numbers than our internal PELs, again, breathing zone exposures and manufacturing workplaces as an 8-hour TWA. So the outdoor standards are tougher to help provide protection for more of the entire population. And outdoor standards for the nitrogen dioxide can be tougher since the ozone forms outdoors. Next slide, please. So how can we reduce this air pollution? We have to think about the mixing of the indoor and the outdoor air, where these contaminants exist, where they're coming from, how they can be brought in, can they be diluted, can we filter, is there some other types of control measures that we can put in air handlers, or a lot of people are putting in UV and other types of cleaning type of systems. When we do indoor air quality investigations, we're definitely looking at temperature, relative humidity, concentrations of carbon dioxide as well as carbon monoxide, oxygen, and different types of particulate matter. The indoor air can mix within different types of facilities by infiltration, natural ventilation, and forced ventilation. And a lot of the ventilation requirements, practices, technical guidelines are in ASHRAE standards. ASHRAE standard 62 Was first thrown out there in 1999. It used to be updated, and now we're continuously updating it. So looking at that, OSHA tried to put out a IAQ standard. It didn't necessarily fly. So a lot of the technical guidelines that we're looking at for this are from ASHRAE. Next slide. So mixing. So here's our infiltration. What is being brought in from the outdoor environment, leakage through holes or opening in the buildings, that can be driven by pressure and temperature differentials, as well as by existing ambient wind speed and direction. Natural ventilation, things we get when doors and windows are open. We don't do that too much, not necessarily in high-rise buildings for sure. And forced ventilation are things that are being driven by our mechanical ventilation system. So how are those designed? How are they operating? What are the pathways, the source and exposure pathways, and how is it being distributed through a building as well as exhausted? All right, next. All right, so if we wanted to look at air quality investigations, just quick, couple of little bullet points for the final 3 slides. We would look at the building history. How was it built? What was it started as? Has it been reallocated to something else? Do a brief walkthrough, use some common sense, and look at what are the building walls and floors. Look at the ventilation system. Ask about symptoms, health effects, things that are reported. You'll get an earful from people that are having symptoms and complaints. EPA has some great questionnaires. The Building Owner's Guide has some stuff. You can, do questionnaires to try to get some of this information quantitatively as well as qualitatively. Do an assessment, look for sources. Some of the basic things we look at air monitoring wise are the CO2 CO, temperature and relative humidity. That tells you how your mechanical ventilation system is operating. Airflows, what's coming in, what's going out, how much supply versus how much exhaust. Is it a positive or negative pressure? Particulates, way different sizes through particle counts or other types of IAQ instruments. Perhaps we're looking at microbial agents and also total volatile organic compounds. Do an investigation, do some monitoring, usually as a relative comparison, and write up a report with some recommendations. Next. What are we going to look at? Outside sources, exterior of the building. Are there cracks? Is there infiltration? What about the HVAC system? Again, how is it set up? How does it operate? How is it maintained? Is there a boiler room? Is there an attic or crawl spaces? Are the spaces occupied? And based on the occupancy, what is the size and the operating conditions of that ventilation system? Wall cavities, if there's been some moisture intrusion or if there's been some flooding, it could be potential for microbial agents in there. And also looking at storage spaces. Next. All right, challenges are, you're not going to see everything and anything. The source is not going to be waving a red flag, and you're not necessarily going to be able to figure out what it is. So you kind of got to look at the whole picture from top to bottom. The problems or the symptoms or health effects may be cyclical or episodic, so they may not occur on the day that you get there. It may be 2 weeks before or a month after. Only a few persons may complain of a problem, but if you start talking to people, you'll usually get a lot more input from the occupants. The situation can also become emotionally charged. Again, there can be dynamics between the workers and the company. Is it a lease space? Is it a space they control? What are the patterns? Again, we've been doing a lot of remote, and now people are coming back to the workplaces, so there's certainly been some challenges associated with that. All right, next. I think is maybe my other information. I referred to a little bit of EPA publications, a lot of stuff out there. The Building Owner's Guide has a lot of information, multiple chapters, and a lot of checklists in the back of the book. The questionnaires, doing a walkthrough with the ventilation system or the building, looking at complaints and patterns, etc. And ASHRAE has a lot of stuff on the ventilation. All right, next slide. I think I did it within a reasonable amount of time. Any questions?
Jan, would you like to briefly just talk about the PDC conference coming up?
Yeah, do you have that slide? Can you show the, my agenda thing? Yeah, so we're doing a joint PDC. We did it last year, Gulf Coast AIHA in association with Gulf Coast ASSP. It is going to be on April the 19th of this year. That is a Friday in April. We're going to a new location. So it is going to be at the Norris Conference Center. It shows that there on the slide. That's kind of on the west side out in City Center over by Town and Country. So this is the website. You can go to gulfcoastpdc.com. This is where you're going to get the registration. We're obviously doing CEUs. There's going to be a whole vendor exhibitor section. Okay, so there certainly is still room for vendors. We clicked on it this morning, and the current registration is $99. It's going to go up as we get closer to the event. So again, it's going to be one day of CEU. In fact, Serena and the Southwest Center are doing the CEUs for the Gulf Coast AIHA. ASSP is also going to do their CEUs through national. So CIH, CSP, you're definitely going to be getting CM points for this. And we have a draft agenda. Do you have the agenda, Serena, or they can just go and take a look at this? So there's going to be 3 safety tracks and 1 IH track. Okay, so there's going to be 4 concurrent sessions that are going on. We're going to gather about, I think, 8:30 or 9. There's going to be a keynote speaker from 9 to 10. Then there's going to be the 4 breakout sessions. So the 4 IH sessions, and then there's going to be 12 safety sessions. One's going to be safety leadership, I believe, is one track. Safety management is another track. We have the IH track, and then the 4th track is professional development. So a lot of good stuff. We're back to face-to-face. We're going to do some networking. A lot of exhibitors are going to be there. And there's going to be a continental breakfast and lunch included, as well as breaks. So it's a good drive-away price for some CM for $99. Jump on and let's get her done. All right, thank you.
Thank you, Jan. Okay, welcome back, everybody. We have 2 speakers from Lawrence Berkeley National Laboratory. We have Chips Hoai, who is a Biosafety Officer at the Lawrence Berkeley National Laboratory. She has over 15 years of experience in the field of biosafety and has been involved in numerous research projects. She has extensive knowledge of biosafety regulations and guidelines and has been instrumental in developing and implementing biosafety programs at several University of California universities, including UCLA, UC Irvine, UC Davis, and UC Berkeley. We also have Julie Jewell. Julie has an education background in microbiology and industrial hygiene, and she has been working in the field of worker health and safety for 10 years. 5 of them are in biosafety. As an industrial hygienist and the Deputy Biosafety Officer at Lawrence Berkeley National Laboratory, she works closely with research scientists, helping them assess the hazards in their work and ensuring their safety and health are adequately protected. So please welcome Chips and Julie.
Hi, everyone. Thank you, Serena, for that great introduction. We're really excited to be here today and talk to you a little bit about some unique biosafety challenges at Lawrence Berkeley National Laboratory, which we'll go on to call either LBNL or the lab at this point. So my name's Chips, and like Serena mentioned, I'm the Biosafety Officer there, and I'm here with my colleague, Julie, who I'll let introduce herself real quick. And I'm gonna actually turn off my camera because I'm doing the slides and I don't want the any connection issues to happen.
Thanks, Chip. Good morning, everybody. This is Julie. I'm the Deputy Biosafety Officer at the lab and one of the industrial hygienists at EHS. Again, really excited to be here and talk to you all about some of our biosafety challenges at the lab.
So we're going to shift gears a little and talk a little bit more about biosafety now. Our research at LBNL, the lab, focuses on discovery science and solutions for clean energy and creating a healthy planet. So after Julie tells you a little more about how the lab started, we'll dive into some of the clean energy research that happens on site, especially some of the bioenergy and biofuels work that requires some biosafety oversight from our group. So some of these research projects present unique IH and biosafety challenges that you might not encounter in your day-to-day normal biological labs. And we just kind of want to get that out there and show you some different experiences that you might encounter that would be unique. So this would include our large-scale fermentation production facilities, as well as we have specialized growth chambers that we call EcoPods. And then last, our advanced light source.
Yeah, so who are we as a lab and what do we do at Berkeley Lab? So Lawrence Berkeley National Lab, or more often referred to as the Berkeley Lab, is actually the oldest of 17 national labs under the Department of Energy. It all really started in 1928 when the young physicist Ernest Lawrence came to University of California, Berkeley campus, where he built his rat lab and invented this particle accelerator called a cyclotron. And that later won him a Nobel Prize in 1959. So as we see on the slide here, the top picture is the very first cyclotron he invented. And as his idea of a cyclotron got bigger, really too big for the rat lab on campus, he moved up the hill. And the picture in the middle, it shows the first 184-inch cyclotron being built on the hill in the 1940s. And the bottom picture, of course, shows what that building looks like today, where we are now, very pretty. But really how it evolved from just a small radiation lab to a national lab with 16 Nobel Prizes and hundreds of breakthroughs. Lawrence's biggest contribution is he actually brought together a team of colleagues in physics, chemistry, biology, engineering, and medicine, all work together to solve big problems. And this multidisciplinary team science approach is really the foundation of our lab. And even today, our scientists from all over the world, they work together to solve global issues in many areas. And our research really goes beyond accelerator technology. We have all the way from discovery science, AI, science, material science, climate research, micro, and of course we have clean energy. And that. All right, so here we've listed some various forms of alternative energy. So we have biofuels, solar fuels, hydrogen, geothermal energy. We not only do research in these areas, but we also conduct research to make sure they are more accessible to consumers and how we can integrate them into the power grid of our nation. So since we're going to be talking about biosafety today, let's take a look at
Okay, I'm sorry about that. I don't know how much I actually came through. So let's go to the next slide, please. So again, let's take a look at the biofuel research. And the goal of bioenergy research is really to develop fuels derived from solar energy stored in plants to reduce our traditional fuels such as gasoline and diesel. So the picture here gives a good illustration of kind of the actual process. So we start with plant materials, or we call feedstocks, and then we break them down into polysaccharides and lignin, which can be further depolymerized into monosaccharides and intermediates of lignin, which will then be converted to biofuels and bioproducts by microbes. But really, genetically engineered microbes come into play in just every stage of this process. We can use these microbes to optimize the production of enzymes to help with deconstruction and depolymerization. And we can use microbes to better utilize these sugars and aromatics and efficiently convert them to biofuels and bioproducts. And we also engineer biosynthetic pathways for producing various chemicals of interest. So that's really a nutshell of the research at the lab. Next, I will turn it back over to Chips, and we'll look at some real-life examples how us IHs and safety professionals help ensure the safety of these bioresearch activities.
So let's say our researchers discovered a plant that's covered in some bacteria. And this bacteria seems to be producing a molecule that's very closely related to another molecule that we find highly desirable, maybe something like one of these biofuels. The problem is this desirable molecule could have a really high energy cost to manufacture. So we want to reduce that and find a solution, a simpler solution. So they want to see if they can take this bacteria and alter it to produce the molecule that we want. Can we even do this? Is it something that we can do safely? So in order to find out, we'll have to do a risk assessment. So this is a standard process that biosafety professionals like to do. And in the biosafety world, can this research happen? The answer is usually, well, it depends. So what we'll need to do is take several factors into consideration. We'll need to identify the potential hazards. Is this work going to be hazardous to the researchers? Is it going to be hazardous to the environment if it got out? Could we possibly have catastrophic consequences to ecology? Are our plants then going to be in danger if whatever we've created gets out into the environment? What about the products that we're creating? If you're making a biofuel, is it something that could be hazardous as well? And we need to take that consideration into consideration when we're doing this work. We'll want to look at the hosts that we're working with. Are they infectious? If so, do we even have treatments available out there to take care of them and keep our workers safe or the public safe? Are our products, and we'll need to think about the type of work activities that we want to perform with these agents. Do we have those laboratory resources available? What type do we have? Do we have the facilities to even perform the work safely? So for biosafety, there are 4 different levels. I'm not sure everyone's extent and knowledge on this topic, but basically there's biosafety level 1, 2, 3, and 4. And as you go up in biosafety level, you're going up in practices and procedures, as well as containment and facilities. And the higher your hazards are, the higher biosafety level you're going to want to work in. So do we have these facilities available to us? What about the equipment? All of this information we're going to have to take together and assess our situation on whether we can do this research. We'll define the risks and characterize them, and then figure out what kind of controls we can put into place to mitigate these risks. So once you've gone through this process with our researchers, and let's say they were able to test out the production of our target molecule. Yay, it worked. Let's say we could produce it, and now that's being done in a small scale. But they want to ramp things up and start producing on a much larger scale. We've just changed the definition and scope of our work activities. So maybe even the lab environment needs to change. We'll have to go through this whole risk assessment process all over again, figuring out our new risks, characterizing those risks, and then mitigating them. Which brings us to our next topic of large-scale biosafety here at the lab. We are fortunate enough to have a facility called the Advanced Biofuels and Bioproducts Process Development Unit, the ABPDU. And this facility is equipped with the capability to conduct fermentations in scale of up to 300 liters. It's a facility where we're moving advanced bioproducts into a commercial scale type level. So sometimes our final products can be harvested for end use. Other times those products are going to be further analyzed downstream by our researchers, whether they're doing imaging with it or further processing to develop it into another product. Our clients of our ABPDU can either be on-site researchers or even outside collaborators. So that's just one of our LBNL core things is we have team science, and we really want to promote that team science. So these users will bring in a wide range of biological materials to culture. Sometimes they're wild type, other times they're recombinant or genetically modified organisms. And this could include non-pathogenic bacteria, yeast, algae, and filamentous fungi. So at the ABPDU, they conduct large-scale fermentations. It can be from a range of 80 liters up to as much as 300 liters, and that's high volumes. That's a lot of material, and depending on what you're working with and the range of biological materials that we could have there in the facility at any given time, could also create lots of different products. So we have a wide range of end products as well. They'll produce molecules or proteins of interest for the food industry, the cosmetic industry, or even pharmaceuticals. So we have researchers producing fruit proteins, for example, that they can then use in sweeteners. We also have some experiments where some plant-based proteins that mimic the taste and texture of meat are being produced. So down the line, maybe this is another way to, get our veggie meats out there. And we even have a project that uses cacao cells, and they're using them to produce a special chocolate component. And who doesn't love chocolate? So there's a lot of really exciting research coming out of our ABPDU. And oftentimes those experiments, these large-scale experiments, involve the genetically modified organisms that have been engineered, such as some of those projects I just described. When that happens, this work now falls under the NIH guidelines for research involving recombinant or synthetic nucleic acids. The guidelines detail safety practices and containment procedures when you're working with recombinant materials. So if you, like most public institutions, have any NIH funding, they're not really guidelines. These are requirements that we have to follow, and they're put in place for several safety reasons. So NIH will come after you if they find out you're not doing what you're supposed to, and you could potentially lose your funding. When you've got large-scale work happening, it is covered under Section 3D6 of the guidelines, which covers experiments involving more than 10 liters of culture. If this particular section of the guidelines applies to your work, you'll need to follow the specifications outlined in Appendix K of the document. This discusses the physical containment requirements for large-scale use. Appendix K also outlines something called good large-scale practices, and you'll need to follow these as well. So basically, in a nutshell, good large-scale practice, or GLSP, is a combination of work practices and facility requirements that need to be met in order to work safely. So our ABPDU is limited to work with only viable, non-pathogenic, and non-toxigenic strains. And these strains would have limited survival if we accidentally release them into the environment. So because of this, we can handle our large scale at biosafety level 1. We won't be performing any fermentations with any pathogenic bacteria or even agents that produce toxins, something like Botox or another biological toxin. So stuff like that is going to raise the biosafety level, and it's going to increase the requirements that need to be met to perform work safely. If you do plan on having research at that level, there in Appendix K that we mentioned in the previous slide, it also outlines the specifications you need to follow in order to work with these larger volumes at either BSL2 or 3 or above. So as the hazards and containment levels increase, you'll have to have additional requirements you need to meet. And now Julie's going to dive into GLSP a little bit further with the work that we do here at the lab.
Yeah, next, let's take a look at some of the things you might want to consider when setting up a facility like this or considering the safety aspects of the research activities. So as you can see in the picture, the fermentation system is pretty complex, and there are many types of hazards present, not just biological.
Julie, I think we're having audio issues again.
Sorry, I didn't unmute. So let's take a look at some of the things you want to consider when setting up a facility like this or considering the safety aspects. And considering the research aspects of these research activities. A fermentation system like this, as you can see in the picture here, is very complex. There are many types of hazards present, not just biological hazard that you deal with in the fermentation, but there are also electrical hazards, steam, hot surfaces, pressure, corrosive chemicals will be used. So to make sure everything works smoothly, good written procedure and training is very crucial. And also, do you have an emergency response plan if something spills? How are you going to make sure you're I don't know why the audio is bad. Chips, do you want to take this? Let me fix. I'll move to a different station.
Sure, sorry, I had to move over. So, okay, so I couldn't really hear what you're saying. So you want to make sure everything works smoothly. You have good written SOPs, and training really is crucial in our large-scale fermentation facility. Do you have an emergency response plan in place for handling spills? Your plans need to ensure no personnel exposure or release into the environment can happen. And this also ties into the next point. If there's a discharge, whether it's intentional or accidental, how is it handled? You'll need to consider EPA and local governing agencies and regulations and have an agreement with them prior. In our facility, we'll later see that we have a waste treatment unit for any discharge, and it's going to neutralize the discharge. So we have an agreement with our local governing agency, EBMUD, which is the municipal utility district. So because we have this treatment unit, it can discharge directly down into the sewer after we treat it. At the end of the fermentation, do you have cleaning processes in place, for instance? So we have something called cleaning in place, and the equipment is actually equipped with, special heat elements that allow us to clean and sterilize our fermenters so that it's ready to use for the next process. Julia, are you ready again?
Is this better?
Yes.
Okay. All right. Really apologize for that. I don't know what happened there. Yeah, I can make this slide. So during the experiments, how do you ensure that you have containment? How do you ensure you're not releasing anything into the lab environment or even the actual public environment? So we can consider maintaining a closed system when we do these experiments or have other containment equipment such as a biosafety cabinet. And during fermentation process, sometimes it's necessary to remove ultra liquid either during the fermentation for sampling purposes or at the end when you get everything out. So how do you make sure things are contained during those processes? So you can either have a closed system for transfer or you can inactivate before you remove things. So on the slide here in the middle, it shows kind of a closed system vessel, which can be connected directly to some of the discharge ports on the fermentation system. And really then you can maintain a closed system and make sure nothing is released. And there are other kind of accompanying hazard in addition to the organisms that you're using. Sometimes there could be toxic or hazardous byproducts or hazardous end products. For example, one of the projects that we've had, their end product was histamine. And, you know, histamine causes allergic reactions in the body. So you really don't want any histamine in the lab getting released during the fermentation or at the end of the fermentation. So filtering any off-gassing ports might be warranted. And I included a kind of a close-up of this kind of red square here. If you take a closer look, that actually allows you to install any exhaust filters that's needed. It could be a HEPA filter, it could be a charcoal filter, depending on what kind of molecules or chemicals you're trying to filter out. So definitely some things that you don't want released into the environment. You want to protect your water against. So that's really kind of large scale fermentation. Again, you look at the guideline, you analyze what biological material you're going to be using, and look at the actual experiment, the equipment setup, and processes and there. Make sure you have enough controls to mitigate this. And next example, we have called the EcoPods. So this is really this is built a Berkeley lab team of scientists. So yeah, EcoPod. So these are, I guess I don't know how much came through. Kind of the fabricated ecosystem. So we started with a very small version of this. We call it the EcoFabs. These are just like the box of a cell phone kind of size containers that can hold a seedling plant and a small amount of soil. And scientists can study the plants or plant interaction with microorganisms in these small fabricated systems. Those are great, but it's a very reductionist way of looking at things. As we know, a lot of scientists doing research in the field know that the actual field is a very, very complex system. But they're also impossible to replicate. So our scientists thought we need something in between. And then there's kind of the birth of the EcoPod system. It is actually a custom-made, entirely custom-made system by a German company with kind of the ideas from scientists. So let's take a look at the next slide. at what these units have. So EcoPod, we can divide it into kind of 3 compartments. We have a top unit where there is irrigation, lighting, ventilation system, some permanent measurement equipment on top. And in the middle, we can see here there's the atmospheric unit, which is actually the space for the plant to grow in there. And the bottom is our soil unit. So we have these stainless steel cylinders that we put soil in, and the plants can grow in the soil. And here we have a scientist kind of doing experiment here, and you can actually, sorry, going back. And you can actually see the size of the EcoPod unit. It's almost twice the height of the scientist. And it's really just a high-tech growth chamber. It's about the size of a Mini Cooper that allows plants to be grown in a highly controlled environment. You can control the temperature, humidity, and other parameters that are of interest for study. And the inner chamber can house a little bit over 0.5 cubic yards of soil. Has room of about 5 feet of atmosphere, enough for the kind of slightly taller plants to grow as well. And we have different sensors that measure above and below ground characteristics. And this really allows the scientists to study synthetic microbial communities, engineered plants, and really allows us to kind of dive into some of the biogeochemical processes across the soil. The next slide, please. So what are some of the safety challenges associated with EcoPods? We start with looking at what kind of biological materials are used in these growth chambers. We can have either wild type or genetically modified microorganisms, plants, insects, and of course we have soil, which we may have permit issues if you're using soil from out of state. Even within California, some regions regulate the soil. And the work process is pretty straightforward. It's basically a very controlled environment to study the interactions among these biological agents. And of course, we have to consider the containment. So we could, like I said, we could use genetically modified organisms. We could also use plant pathogens that may be of interest to some scientists. So we want to make sure these agents are contained as well, not get released into the environment. So in our second version, we have 2 versions of the EcoPod. In our second version, where the scientists would use genetically modified organisms, we actually have HEPA filters on top of the unit, so it can actually filter out anything and prevent them from getting released into the lab. And another challenge we had was soil change. You saw previously we have these stainless steel cylinders that contain soil, and it could be very, very heavy with the lacinider and the soil together. So how do we safely dump out the soil after an experiment and make sure nobody's hurt and no dust flying around, because there could be organisms in the soil as well. So how do we make sure that
part is done safely. We actually came up with idea for a HEPA vacuum that can be used to suck the soil out from the stainless steel cylinders after an experiment. So we make sure everything is contained with a HEPA vacuum. And cleaning, decontamination, the lysimeters that contain soil need to be cleaned and decontaminated, of course, because they contain biological. So you can actually do bleach and ethanol and wipe the inside of the cylinders. And the growth chamber itself, the atmosphere unit, you can actually heat it as well, increase the temperature to kill some of the organisms, and you can also wipe it. And waste disposal. So how do you make sure the large amount of soil is disposed properly? We have considered sterilization in place, but it wasn't quite feasible at our facility, so we have to dispose of everything as biological biohazard waste. So make sure you have a vendor, waste vendor that can take this type of waste. And transportation, installation, like I said, these units are very tall. It could be 10 feet or higher, and that's taller than any typical lab that we have on site. So figuring out a space that we can actually put this in was a challenge, and the scientists came up with a kind of creative idea, and we were utilizing the loading dock of a research building, and with a forklift to haul this thing in and out of that space. So we actually kind of retrofitted this loading dock space into a biological lab. It has key card access. So we have controlled access. We have emergency eye wash and safety showers. We have chemical storage cabinets. So it really kind of turned into this BSL2 space that can allow this type of research to happen. And of course, ergonomics, these lysimeters, the unit itself is they're all very, very heavy. So how do we make sure kind of during installation and during manipulation of these parts can be, people are not going to get hurt. So we use tools and equipment such as pellet jacks to help us lift some of the heavy parts during experiments. So really, a lot of times we look at kind of the specific operation, and we have to kind of sit down and really look at each type of hazard, come up with controls to mitigate those. And a lot of times you have to think outside of the box and have creative solutions for some of these unique challenges. Yeah, back to you, Chips.
Thanks, Julie. So our final operational scenario we have for you today is also one of the most unique facilities we have on site. We are fortunate enough to have something at the lab called the Advanced Light Source. As Julie mentioned earlier, Ernest Lawrence invented the first cyclotron. So the ALS is actually a third generation synchrotron, which is a type of circular particle accelerator. It uses magnetic fields to push particles around in a fixed closed loop. And this process generates bright beams of X-rays that we can then use for scientific research. Electron bunches get accelerated until they emit bright ultraviolet and X-ray lights, and which we can then direct down to our beam lines to experiment end stations for imaging purposes. So we can image things at the atomic and molecular scale. So we can see three-dimensional structures of proteins, or even view live interactions between molecules within cells. And this allows us to better understand biological processes, things that we can't normally see with the naked eye. So what we see with our eyes is limited first by the light that illuminates the object that we're looking at. And it also is limited by how our eyes perceive what it is that we are seeing. So our eyes can only interpret light in the visible region of the electromagnetic spectrum. That visible region is really just a tiny fraction of this entire spectrum. So what the ALS does is it allows us to use more of this spectrum. From hair-thin beams of electrons that are sped up, it produces light in the form of X-rays that are accelerated to nearly the speed of light. So the speed of light is about 299,792,447 meters per second. Just to give you an idea of how fast that really is, if you were traveling that speed, you could actually go around the world almost 7.5 times in 1 second. So these particles, these electrons are being sped up and spun around this cyclotron at really high paces. After going through that first ring, the electrons are then stored in a second 200-meter ring guided by a series of magnets that force them into a curved trajectory. As they travel around this second storage ring, the electrons emit synchrotron radiation. So this is energy in the form of photons. Those photons then get directed to specialized optics down a 12-meter long beam lines, and at the end of these beam lines are experiment end stations, and this is where our imaging happens. The ALS has 40 different beam lines, and each of them are at different wavelengths, and so they allow for different types of imaging. The wavelengths of light span the electromagnetic spectrum from infrared to X-rays, and they have just the right size and energy range for examining the atomic structure and electronic structure of matter. So these two kinds of structure determine nearly all of the commonly observed properties of matter, such as strength, chemical reactivity, thermal and electrical conductivity, and magnetism. Out of the 40 beam lines that we have, only about 10 of these are actually currently being used for imaging biological materials. And these 10 beam lines are also scattered about the facility. So they're not all clumped into one area or one zone that we can kind of control. They are all over, so we have to take biosafety into consideration for the entire facility. And that's because of the layout we have in our ALS. So our advanced light source, to give you an idea, is one large open space. And you can kind of see in that drawn image of what the ALS looks like. And we also have an image of just one tiny section there of the actual lab space. So it's one large open space, and that introduces many challenges for us in terms of imaging biohazardous materials. In some cases, these beamline end stations end into what is a hutch. It's an enclosed space, but really that hutch isn't there for the protection from biological materials. It's there because the beam lines are open, and we want to protect our users from radiation. So we have to think about the types of materials and manipulations that we can do when you're in an open situation like this. Where can you safely prepare your samples, for instance? There's multiple beam lines, and they're running at the same time, being operated by users, some that are aware of the research you may or may not be doing, some that are not. And these users have various levels of differing levels of training for the facility. So where can you handle them safely? Are your samples going to be prepared in this large open space, or do you have other facilities available nearby where you can keep your materials contained and isolated from the other users when you're performing those riskier procedures? When you're in this open environment, you'll need to consider what could be happening to your materials as you image them. You've got this beam of energy being shot through your sample. Is it going to aerosolize it? Are you working with something that's potentially infectious, for instance? And then once that gets aerosolized, can it then spread your organism and contaminate the entire facility? As you can imagine, having a situation like that would not be good for such a large open space, because decontaminating everything would not be an easy task. So then what types of biological materials can we use at our ALS? The biological sciences research that happens here can be divided into two areas. We have the general biology, which is our microscopy and spectroscopy, and then we have the structural biology experiments, so our crystallography and diffraction. Our users will bring their biological materials, like the human cells or their recombinant DNA materials, maybe bacteria. We have viruses coming in. Sometimes there's parasites, biological toxins, plants, soils, and other environmental samples as well. So sometimes these materials, like our human cells or pathogenic bacteria, can pose increased risks. So we need to think of solutions to bring those risks down to acceptable levels, so that we can actually even perform this research in this type of facility. So for instance, some of the recent work at the ALS includes studies where cells that have been infected with SARS-CoV-2 have been imaged using soft X-ray tomography. Before these researchers get started taking a look at these cells, though, we had to make sure that it was work that could even be done and done safely at our facility. And that's where our risk assessment comes in. So users of the facility need to complete a form called an ESAF. It's an experiment safety assessment form. And this form describes the type of work that they want to perform at the advanced light source. Once they complete the form, it gets reviewed by a safety team that is dedicated to the facility, and that team then works closely with us here in EH&S. Having this form allows us to watch the gate and make sure we can filter in the type of work that can be done safely. It helps us to identify the risks of the work our researchers want to do, so we can work with them to find solutions on how to do it without putting themselves at risk or anyone else in harm's way. So for instance, like those cells that were infected by SARS-CoV-2, they had to complete an ESAF, and all of that got reviewed, and we had to have a discussion with our researcher on the type of work that they could do. Since our facilities aren't really equipped to image highly infectious and pathogenic materials out in the open space, we had to ask them if they could chemically inactivate their samples, for instance, before they bring them into the facility. So by doing that, our users are able to safely take a closer look at these cells. In some cases, that's not a possibility in activating the materials. So we have to find solutions to figure out if there are ways to actually image live infectious materials. So in cases like that, we'll have standard operating procedures in place and safe practices to make sure these agents that come into our facilities come in a cleaned manner within sealed secondary double containment that never gets opened at the ALS. So we'll have them, do experiments to make sure these containers are completely sealed, and everything has to be disinfected and in a condition where it's safe to handle even by your bare hands before bringing into our facility. When looking at the ESAF and doing our risk assessment, some of the things you'll want to take into consideration include training. So not only training of the users, it could be beamline specific training. It could be training on the safe use of the equipment itself, because each of our beamlines runs differently. There are scientists that are specifically in charge of each of the beamlines, and they have their own practices and procedures and ways to use their equipment. And then you'll want to consider, do they even have the biosafety training for doing this type of imaging work? You'll also have to consider the type of training that goes on around the facility as well. Anybody in the area should be made aware of whatever hazards are being brought in, for instance. There are situations where you may need to wear a dosimeter to track the levels of radiation that you're receiving in our facility. So if you, for instance, at your home institution have a dosimeter, you'll also have to get one at LBNL that's specific to us, and it'll be tracked that way as well. Another thing you'll want to consider are the hazards of the materials. Like I said, in some instances, maybe you can inactivate them before bringing them in first, and that's going to lower the hazards. But maybe you need to bring something live because you want to actually image and see interactions in real time, for instance. So in that situation, perhaps we can accommodate that research by double containing things in a certain way. You'll need to think about the transport of the materials. How do you get them into our facility safely? Are you using the proper containment? Are you hand carrying them? Do they need to be shipped from an outside institution? And if so, are you following the proper shipping protocols? If it's something infectious, we'll want to make sure that you're not opening that package in the ALS because we can't properly contain it there. You'll have to have a procedure where you can open it within a biosafety cabinet to make sure your package hasn't broken during transport, for instance. And then you'll want to disinfect it before bringing it into our facility. Then you'll want to consider loading of the samples. So if you're working with something infectious, like I mentioned earlier, a lot of these beam lines don't have any enclosures. And so if you have something that's being imaged out in the open, is that going to be too risky? Containment for imaging of biohazards in an open space, like I mentioned, there are some situations where you have a hutch and that is completely sealed in. So while you're imaging, you don't have direct access to the agents. But in some spaces, the beam lines are just out in the open for everybody to potentially walk into. So in those cases, if there's a process where maybe some aerosols might be produced, you can consider using localized HEPA filters to help mitigate those risks. Then there's also the issue of decontamination. How do we decontaminate? What do we use for disinfection? Some of this equipment is very sensitive, so you'll want to make sure that you select the appropriate disinfectant for your techniques that won't damage our instruments. But you also have to select ones that are going to be appropriate for whatever agents that you're bringing in. A lot of times our ALS users will use 70% ethanol, but depending on what you have as an infectious agent, that might not be appropriate. So we have to come up with solutions and think about different ways to contain these organisms where we don't need to worry so much about disinfecting the equipment after imaging. And the final thing you want to consider is waste disposal. So what do we do with this waste when we're done? For the most part, our users tend to bring everything back to their home laboratories and dispose of it appropriate there as biological biohazardous waste. But we are actually working at the ALS to have a small program where there will be waste collection on site for certain situations, and we can directly get rid of it there by having a vendor like such as Stericycle take the biohazard waste for us. So those are just some of the safety challenges that we've encountered and had to deal with at the Advanced Light Source.
So to close things up, we want to bring you back to the fundamental, which is risk assessment. And as you can see from all three examples, that no matter what your operation is, what kind of materials you're working with, the process of risk assessment does not change. You always look at what you're handling, what's the activity and the lab environment that you're dealing with, define the hazard, and then define the risk. Sometimes hazards are the same, but the risks are different depending on how things are handled or where things are handled. So you always do that risk assessment, analyze the risk, and come up with controls that are compatible with your operation and can mitigate the risks. And we're really fortunate to work at the lab where there are a lot of cool research, innovative ideas, and cool equipment, but at the same time, they also present unique challenges in the areas of safety. But that really also makes our jobs interesting every day. So I hope that was helpful for everybody here. And we're happy to take questions if there are any.
So here's just a couple of sources.
Hello. Yes, my name is Bill Young. I was going to ask you, so, and I'm assuming you're looking at things, using that X-ray light and things like that are very, very small. And I was wondering, it seems like you're pretty heavily reliant on the efficiency of a HEPA filter. And I was wondering, do you evaluate the risk of things penetrating through the filter for the size dimensions that you're using, or is that usually part of the process?
So usually the HEPA filter is actually one of the last lines of defense for us. Typically, we try to, most of the stuff that gets imaged in the facility is lower risk, where we aren't as concerned with the aerosolization. So it's done at BSL-1. But in those cases where it is more hazardous, we tend to try to go towards secondary containment and really not even allowing aerosols to become an issue. I think the HEPA filter is more just like a backup kind of thing to have.
Thank you.
If there are no other questions, I guess we can close this seminar series. Thank you again to all our speakers. We greatly appreciate you volunteering your time for this. And if you, again, our next IH will be in June, I think June 13th, speakers and topics to still be determined. So thank you, everyone. I guess, again, if there are no questions, and have a wonderful afternoon.